All right, so now we finally get to what I think of as the meat of chapter two. So this is the one thing that you're really going to have to carry forward with you for the rest of the course, and that is transformations on base functions. So what we're going to be doing through the next, what is it, 8 parts of this lesson, is we are going to slowly make our way through y equals a, f of b x minus c plus d. So this is going to be our overall goal, and we're going to go slowly by learning what a does, what b does together, c does, what d does together, and then all of them together. So the first thing we're going to look at is this a value. Now this a value, just to give you a preview of what it does, is it can vertically stretch or shrink your graph. If you look at these two examples, this is giving you the same base function. So this black graph is our base f of x function. And if you look at the transform function, so the green and the blue, we're going to talk about one of these being a vertical stretch and one of these being a vertical shrink. Can you guess which one's which? Well, hopefully you're looking at this guy and thinking, oh, the y values got stretched. This one is your vertical stretch, and this one is your vertical shrink. Why is that? Well, for this one, it's because the a value is greater than 1. And when the a values are greater than 1, your graph is always vertically stretched. When the a value is something between 0 and 1, the graph is vertically shrunk. Now I'm a little against this whole shrink word. I don't know why the textbook loves it. I love the word vertical compression. I like a stretch and a compress. The shrunk thing, I'm like, well, it's not the whole graph shrunk, but I guess it is a vertical shrink, whatever. But it's just terminology. So this graph, this textbook really likes that if the a value is greater than 1, you'll see a vertical stretch, and if the a value is between 0 and 1, you'll get a vertical shrink. To really help drive this home, what I'm going to do is just show you a demonstration on Desmos so you can really kind of internalize this. So here's my base function. This is y is equal to x to the 5 plus 3x squared minus 1. This is an odd function. And what I'm going to do is I'm going to put in different values for a. So I'm going to start by putting in a 2. And hopefully you can see that the graph got stretched vertically, right? It's reaching higher in its y values. It's getting further and further away from the x-axis. If I do this again and I put in a 4, let's say, it's even more vertically stretched. If I go crazy and I put something like a 10, then it's going to get extremely vertically stretched away from the x-axis. Now I'm going to zoom in a little bit just to make some of these points just a little easier to see, because I want to talk about how you would do this. So for example, with this one, when you had a point here, let's just say it was perfect. Let's say it's at -1, 1. When you have this vertical stretch, it's something happening to the y values. Hopefully you can see that when the y value or when the a value was a 2, it went from 1 to 2. When the a value was a 4, this point went from 1 to 4. It's a little bit above because it was a little off. And when this went from 1 to 10, right, then all the way up here, this guy's just a little bit higher than 10. We are taking all of our y values and stretching them by a factor of a, which at this point is making them go higher and higher up the scale. What we're going to do now, there we go. Sorry, I just wanted to change that x-axis. It was driving me crazy because it was so compressed. So now we've looked at the vertical stretch. What I'm going to do now is look at the vertical shrink. So what I want you to notice is that I'm going to put in a value like a is equal to a half. Now this point here that's, kind of almost at 1, if I shrink it by a half, it should go to about a half. Right? Now, not perfectly because it's not a perfect point, but there you go. This purple graph, I took that base function and now it's shrinking in its y values, which is bringing it closer and closer to the x-axis. If I went even further and put something like a fifth in here, or let's say a quarter to keep the same pattern, right? This black graph, it's even more shrunk. It's more compressed towards the x-axis. If I go crazy and I put something like a tenth in here, whoa, it's like almost flattening out along the x-axis. So I really want to drive home when that a value is greater than 1, you get that vertical stretching, and when that a value is greater than 0 but less than 1, you get this vertical shrinking. So back to our note. How do we get the transformation? Well, the y equals a f of x can be obtained by multiplying the y coordinates of each point by a, right? So when it was a 2, they stretched by 2. When it was a 4, they stretched by 4. When it was a half, they shrunk by a half. So now we've got these questions, and I've followed the flow of the textbook so that the questions in the textbook will perfectly match these. And the first thing they do is get you to describe how the graph of the function can be obtained from one of the basic graphs, and then potentially you could also graph the function. So they do this because where we're going to get to is graphing totally random piecewise functions where you don't have an equation and you have to really understand the transformation. But they get you to start here in something safe where you're like, okay, I could check this with a table of values and make sure that I've graphed it properly. So first off, what is my basic graph? Well, my basic graph would be my square root of x function. If you're not sure about your basic graphs, don't forget that they're on your formula sheet. You have 7 basic graphs: linear, quadratic, cubic, square root, cubed root, rational or reciprocal. I really like rational functions, and I was calling them this all the way through because that's what we call them in Math 50. But this textbook calls them reciprocal functions because actually taking a reciprocal can be a transformation that we don't do. But anyway, both words are interchangeable. I do not care which one you use. And then lastly, absolute value functions. So these are your 7 base graphs you have to choose from. And this one's going to be the y equals the square root of x graph. Now, maybe let's start with the graphing part, and then we will describe how the graph can be obtained. So to graph your basic function, y is equal to the square root of x, hopefully you remember how to do this from whatever one, I think we did it in 2 point something, right? But you want a table of values. When you're graphing a square root graph, you know that your domain has to be greater than or equal to 0, right? Because you can't take the square root of a negative number. So we're going to pick 0, and then we're going to pick perfect squares. So like 1, 4, and 9. And then the y value is just going to be the square root of that x value. So 0, 1, 2, 3. You don't need to put your base function on here, but if you want to for visual purposes, you can. So 0, 0, 1, 1, 4, 2, and 9, 3. And now we're going to look at what happens when we add in this a value of 3. Now, hopefully you're already thinking that it's a vertical stretch by a factor of 3. But if you're not, or you're not too sure what to do, let's do a table of values. When we do the table of values for our transformed function, the first thing I want to ask yourself is this a transformation on x or y? Well, we already said this is a vertical stretch, and what that means is that your x values aren't going to change. So we're still going to use 0, 1, 4, and 9. This is not a transformation on x. So then what you do is you plug in those x values. So 3 times the square root of 0, 3 times the square root of 1, 3 times the square root of 4, and 3 times the square root of 9, and then you solve. 3 times the square root of 0 is 0. 3 times the square root of 1 is 3. 3 times the square root of 4 is 6, and 3 times the square root of 9 is 9, right? 3 times 3. So this is what my new points are going to be. So if I plot this, I've got a point at 0, 0, 1, 3, 4, 6, and 9, 9. And then we're going to describe what we've done here. So what did we do? Well, what I really want you to notice is that when you have this value of 3 outside, it was a transformation on y. And if you look here, you can see that all of the y values got multiplied by 3. We call this a vertical stretch by 3. Now, using the wording in the textbook, I'm just going to cheat and look here. They say start with f of x is equal to the square root of x. And then they say stretch it by multiplying each y coordinate. I really have to look at this wording. This is new to me. By 3. That's great. Okay, so start with the graph of y equals square root of x, and then you're going to stretch it by multiplying every y coordinate by 3. Now, I had to look at the answer key to see how they wanted to write it. I mean, if I was to say to describe how the graph of the function can be obtained, I would just be like vertically stretched by 3. That's good enough. But the wording they use in the textbook is actually kind of great. It's more step by step. It's like you're going to start with your base graph. Cool. And then you're going to stretch it by multiplying every single y coordinate by 3. Awesome. All right. Next type of question. So the next type of question the textbook asks is simply the describing part. Describe how the graph of the function can be obtained from one of the basic graphs. So for this guy, we've got h of x is equal to 2 over x. First thing you have to ask yourself is, what is your base graph? So I'm going to rewrite this as 2 times 1 over x so that you can see that my base graph is my reciprocal function. So for this one, again, you're going to say start with h of x is equal to 1 over x, and then you're going to again stretch it by multiplying each y coordinate. This feels too long to write. This time by 2. Okay, and again, if you just write vertical stretch by 2, that's fine. Like, that can replace this whole sentence. So the thing I want to see is that you know your base graph, so you're starting with the reciprocal base graph, and that you are stretching it by a factor of 2. Add in the vertical, right? So it's really key, like, to say vertical, they say that you're multiplying the y coordinate. That means that it's a vertical stretch. So this is the textbook wording, right? Stretch it by multiplying each y coordinate by 2. If you wanted to change that, you could say start with the reciprocal base graph and then vertically stretch it by 2, which means you're multiplying the y coordinates by 2. All right, pause the video and give this one a go. So this one, I'm going to say start with g of x is equal to the square root of x. And then what? What would you say for this one? So I left it. The 2 I did was stretch. So what's this one going to be? Well, the textbook likes to say shrink it. Now we could say shrink it vertically. Oh yeah, the textbook added that in. Stretch it vertically. Stretch it vertically. They did throw that in. Man, they really overkill the sentence. So shrink it vertically by multiplying, again multiplying, each y coordinate by 1/3. So it is really key that you're shrinking it. You're shrinking it because you're multiplying by a fraction, right? You cannot read my writing, I'm sorry. This is really hard to write on this board. But something along those lines. If you just said shrink it vertically by a factor of 1/3, I'm okay with that. But really you're shrinking it by a factor of 1/3 because you're multiplying each y coordinate by 1/3. Next thing the textbook likes to ask is write an equation for a function that has a graph with each of the given characteristics. So the shape of y equals the square root of x, and then you want to stretch it vertically by a factor of 8. So we're going to write this as a function, first off. And it's my base absolute value function. If I want to stretch it vertically, you just chuck the 8 out front. That's it. For this one, again, I'm going to write it as a function. So this is my reciprocal function. I want to shrink it vertically by a factor of 2, which is quite different. So this one we talked about shrinking and that we were multiplying by 1/3. This one says that we are shrinking it by a factor of 2, which means that you would be multiplying by 1/2. Okay, so the wording, I find that sometimes they even switch sometimes. Some textbooks will say shrink it by a half. They're saying shrink vertically by a factor of 2, and because that word shrink is in there, they're assuming that you're knowing you're making it smaller by multiplying by a half. But the key thing is you're going to start with your reciprocal or your rational function, and then you're going to multiply that by a half. So then you would rewrite this as 1 over 2x, and that would be your final answer. The next parts we're going to do is kind of more the parts I like, where we're actually going to transform base functions, and we're going to do that via points. So for example, if you have a 0.28 on your base function, I want you to find the corresponding point on a transformed function, which will be g of x. So your base function will be f of x, and your transformed function will be g of x. So it will be written as g of x equals 2 times the f of x function. Now, because the 2 is out front, that means that this is going to be a vertical stretch by multiplying the y coordinates by 2. So you're going to take the y value and multiply it by 2. So if you have a 0.28, you're going to stretch that y value by 2. Your new point will be 216. Same thing here. This one's going to be a vertical shrink by a factor of 4, or you're going to say that I'm going to multiply the y values by a quarter, or you can just say I'm going to divide the y values by 4. Both of those are great. So again, if I start with the 0.28, if I divide that by 4 or multiply by a quarter, my new point would be 2, 2. So that when you are transforming base functions, so we no longer have an equation that we can plug our x values into and solve for y, we just have to take our key points. Now your key points are going to happen anytime your graph goes from an increasing, constant, or decreasing function. So here we have a point at negative 5, 0. Then we would have a point here at negative 1, 4. Then again here at 1, 4. And then lastly here at 4, 1. Now we're going to transform all of these points by vertically stretching them by a factor of 2 or multiplying the y coordinates by 2, right? So you can describe this transformation now and you can do the transformation. So I haven't asked you to describe here, I'm just asking you to do. So you're just going to take all your y values and multiply them by 2. So my new graph is going to have a point at negative 5, 0. That one didn't change. Then it's going to have a point at negative 1, 8. Ooh, that one got stretched. It's going to have a point at 1, 8. Again, stretched. And then it's going to have a point at 4, 2. Again, stretched. And then ideally you've got a ruler. I do not on the screen, so I just have to try to connect my dots. Here, here, and here. So you can visually see that this graph has been vertically stretched by a factor of 2. All right, why don't you pause the video and give this one a go. Same base graph. Only this time we're multiplying our y values by a half, or we're dividing them by 2. So we call this a vertical shrink by a factor of 2, right? But what it's actually going to do, this time let's write times a half, just to switch it up. Our new point will be negative 5, 0, negative 1, 2, 1, 2, and 4.5. So let's plot these, negative 5, 0, negative 1, 2, 1, 2, and then this guy is just going to go half as high. So now you can see visually the difference between a vertical stretch and a vertical shrink. All right, that is the first video. Go and practice.